Hi everyone. In this lesson, we're going to learn about electric fields. The electric field is a vector that represents the force per unit charge that a charge would experience at any point in space. The units for electric field strength are newtons per coulomb. An electric field can be thought of as a map that will tell us in what direction and with what strength a positive test charge will be pushed. So let us imagine that we have a positive charge here. If I were to place a test charge here, a test charge by definition is an infinitely small positive charge. And it's not actually there, it's just hypothetically there. We're thinking that it's there and imagining what would happen to it. It would be forced in this direction. Now the force on it would depend on the electric field. And so the formula is E is equal to F over Q. Now if I had a bigger test charge here, the force would be bigger, but I'd be dividing by a bigger charge, and so you can see the electric field is independent of the size of the test charge. Now to draw a complete electric field, we'd want to imagine test charges all around this positive charge and see which way they would be pushed. Now we're getting a feeling for what the electric field looks like around a positive charge. To tell the strength of the electric field created by a point charge like this positive charge at any distance away, we could use that formula E equals F over Q. The force could be found using Coulomb's law. Let me call the charge that's creating the electric field capital Q and the test charge lowercase q. So we have K capital Q lowercase q over R squared, Coulomb's law, divided by that test charge. You can see the electric field created by a point charge is equal to kq over r squared. The further we get away from the charge, the weaker the electric field. We're expected to know the shape of electric fields around certain charge configurations. The first one is a positive charge. If we were to sprinkle test charges all around this positive charge, they would all be repelled from it, and so the electric field would look something like this. If we were to try to compare the strength of the electric field at different points, let's say point A is here, and B is here, and C is here, the way we tell the relative strength of the electric field is to see how closely together the electric field lines are packed. So you can see at A they're more densely packed than at B, and certainly at C they're the least packed. And so I'd say the electric field at A is greater than the electric field at B, which is greater than the electric field at C. We're also expected to know what the electric field around a negative charge would look like. If I were to sprinkle positive test charges around a negative charge, they would all be attracted to that negative charge. Now comparing these two charges, I would say that the charge of the positive one must be larger than the charge of the negative one because I drew more electric field lines. There's not an exact rule for how many electric field lines to draw, but in general, we'll draw them in proportional to the amount of charge. These are a little better pictures for what the electric fields around positive and negative charges look like. Next, we have to think about what the electric field lines would look like around systems that contain two charges. So let's say we had two positives. If I were to place a positive test charge here, both of my positive charges would repel it. Same idea here. If I were to place a positive charge here, it would want to repel in this direction, but this charge will eventually have an influence on it as well. And so in the end, it's going to be curving upward. So we can draw that symmetrically on the other side. For a charge here, it would be a compromise between this arrow that points directly to the left and this arrow that points to the right and then upward. And so we're going to get this curvature like this. And we can fill in here. And because it's perfectly symmetrical, we can just flip all these pictures over the x-axis and we end up with a full map of our electric field around two positive charges. For two negative charges, it would just be the same picture, but the lines would all point towards the negative charges. So you can see from our last few examples that we could probably come up with some general rules for what electric field lines look like. Electric field lines will always start at a positive charge or infinity. They will always end at a negative charge or infinity, and they will never cross. Here's a better picture of what the electric field lines would look like around two positive charges or two negative charges. If we had a positive charge near a negative charge, and we placed a positive charge here, it would repel from the positive charge, but then the negative charge would start attracting it as it got closer to it, and so we end up this curvature between the positive and the negative charges. The picture on the right shows a special configuration called parallel plates, where we take a metal plate and charge it positively, and another metal plate and charge it negatively, and pull them close to each other. You'll notice that the electric field lines point parallel to each other as they go from the positive to the negative plate. This means that the electric field strength over at this point, or this point, any point between the parallel plates, the electric field is the same. The only exception would be on the edges where we have this curvature. Those are called edge effects, and the electric field would be a little weaker and change as you go from the positive to negative plate. Since many of our experiments rely on parallel plates having uniform charges between them, many of our questions will say ignore edge effects. We also need to know what the electric field looks like in and around a conductor. So let's say we have this spherical metal object that we place a charge on. It doesn't matter if it's positive or negative. That charge is going to try to separate as much as possible. So if it were electrons that we placed on here to make it negatively charged, those electrons would move outward as far as they could and all reside on the surface. If it's positive, we know positive doesn't move, the electrons would move, but still the positive charge would reside on the surface of the sphere. Now you'll recall when we talked about gravity, we talked about how if the Earth hypothetically were a shell of mass, and we were to go inside of that shell, that the acceleration due to gravity everywhere inside that shell would be zero, because there would be mass above us, but equal amounts of mass below us that were pulling on us downward, and overall the entire force of gravity would cancel out. Well, we have the same situation happening here for electric fields. Everywhere inside of this electric conductor, the electric field is zero. Everywhere outside of the conductor, we can act as if all that charge were concentrated at the center, and it's the same as if it were a point charge. So the electric field would look like this around this conductor. Now, I didn't do such a good job because one of the rules is the electric field lines must leave a conductor perpendicular to the surface of that conductor. So let me fix that a little bit. Let's say this conductor here had a radius of capital R, and I wanted to graph what does the electric field look like as a function of R, our distance from the center of this conductor. So here I'll put capital R, so that's where the conductor ends. Everywhere inside of the conductor, the electric field is zero, so I'll draw that here. And then everywhere outside the conductor, we can treat this as if it were a point charge with all the charge at the center. And we know the formula for that one would be KQQ over R squared. So this is a curve that's an inverse square law. This is proportional to 1 over R squared. And its exact value right here would be KQ, the charge on that conductor, over capital R, the radius of that conductor. Example number 1 is going to have a bunch of questions based on this similar setup throughout. So my suggestion is you try all the parts of this question on your own, pause the video for a minute, and then come back and see which ones you got right. If you get one wrong, I would hit pause again and try to do the remaining ones again, because sometimes the answer from one comes from the question before it. An electron is placed at point B between two parallel plates shown on the right. The electric field created by parallel plates is directed. So you'll notice that the bottom plate is positive and the top plate is negative. If we were to place test charges in between them, they would repel from the positive plate and attract to the negative plate. And so the electric field line between these plates looks does. The electric field lines between these plates look something like this. So the answer is A, upward. An electron is placed at point B between the two parallel plates. The electric force on the electron is directed. Well, if we placed an electron at point B, the electron is negative. It would repel from the negative plate and attract to the positive plate, and so the force on it would be downward towards point C. If you picked A, you forgot that the electric field shows the direction of the force on a positive charge, and so an electron actually goes in the opposite direction as the electric field lines. An electron is placed near the negative plate and moves towards the positive plate, passing through points A, B, and C. The electron will experience the greatest force when at. Well, the electric field is uniform between the parallel plates, and so we have this formula E equals F over Q. If the electric field is the same everywhere and the charge of the electron is constant, then the force on it must be constant as well. Choice D. An electron is placed near the negative plate and moves towards the positive plate, passing through points A, B, and C. The electron will experience the greatest acceleration when at. So according to Newton's second law, if the force is the same everywhere between the parallel plates and the mass of the electron is a constant, then the acceleration must be constant as well. An electron is placed near the negative plate and moves towards the positive plate, passing through points A, B, and C. The electron will experience the greatest speed when at. For this one, we just said that it was accelerating the entire time from the negative plate to the positive plate. So it's getting faster and faster and faster as it travels towards the positive plate, and so the correct answer is choice C. An electron is placed near the negative plate and moves towards the positive plate, passing through A, B, and C. The electron has the greatest kinetic energy at the positive plate where it's traveling fastest. The electron is placed near the negative plate and moves towards the positive plate, passing through A, B, and C. The electron has the greatest electric potential energy at the negative plate. So basically, as the electron traveled to the negative, from the negative to the positive plate, it was losing that potential energy and gaining it as kinetic energy. An electron is placed at point B. It would take positive work to move the electron to. Now you have to be very careful with the wording of work questions. This question is asking about the work you would have to do to move it from B to A or from B to C. If I were to move it from B to A, I'd be fighting the electric force. And so I would have to apply a force in this direction and move it in this direction. Therefore, the work would be positive. If I wanted to take it from B and place it at C, well, it naturally would slide from B to C because of the electric field. But it would slide right past C and go to that positive plate. And so I would have to apply a force upward as it moves downward to go from B to C. And since those two vectors are in opposite direction, I would be doing negative work. The answers to these questions would be different if I asked you about the work done by the electric field, as opposed to the work done by the external agent, like myself moving the charge. Compared to an electron, if a proton were placed at point B, it would experience well, both an electron and a proton have the same charge, just the opposite sign. So if I place the same magnitude of charge in the same electric field, the magnitude of the force will be the same. This question asks about the acceleration of the proton compared to the electron. We just said the force was the same, but when we look for the acceleration, we use Newton's second law. When we have the same force, a proton has a much bigger mass, and so it will have a much smaller acceleration. In this problem, we're expected to find the electric field due to charges 1 and 2 at point A to start. So the first thing I want to do is figure out the direction of the electric field from charge 1. Charge 1 is a positive charge, and so at point A, a test charge would be repelled to the left. So I'll call this E1, the electric field, just because of charge 1. Charge 2 over here is also a positive charge, so it would also create an electric field to the left at point A. I'll call that E2. And you don't necessarily need this for this problem, but you'll see that I made E2 smaller than E1, and I know that's the case because even though Q2 is twice the charge, it's much further away than charge 1 from point A. So since they're both to the left, I consider to the left to be the negative x direction, and so I'm going to say that the electric field is going to be negative E1 minus E2. Just giving them negatives to indicate that they're directed to the left. So for each of those electric fields, the magnitude will be K Q over R squared. I think it's a little easier if we pull the negative K out. All right, now I'm ready to sub in some numbers. The 5 microcoulomb charge is 15 centimeters away, so I'll make that 0.15 meters. And the 10 microcoulomb charge is 45 centimeters away, so 0.45 meters. Plug this into the calculator, you'll get negative 2.4 times 10 to the 6 newtons per coulomb. We decided to make left to the left to be negative, but I don't think that's necessarily a rule you have to follow, so it's probably best if we make it clear to everyone that this is 2.4 times 10 to the 6 newtons per coulomb to the left. Now we're asked to find the electric field due to charges 1 and 2 at point B. So at point B, directly in between these two positive charges, E1, if I make that the electric field created by charge 1, will be smaller than the electric field from charge 2 because that point is equidistant to both the charges, but charge 2 has a larger magnitude, larger charge. So I think my answer should turn out to be negative, indicating that the total electric field is to the left. So to find that total electric field, I'll write E1 because it's to the right, minus E2 because it's to the left. So that's K Q1 over R1 squared minus K Q2 over R2 squared. This time these R's are the same, so I can just drop the subscripts. That allows me to pull out the K and the R squared and the negative sign. Now I'm ready to plug in some numbers. I guess I shouldn't have pulled out a negative sign. Let me erase that. And so now Q1 is 5 times 10 to the negative 6 coulombs, and Q2 is 10 times 10 to the negative 6 coulombs. Plugging that into my calculator, I get negative 2.0 times 10 to the 6 newtons per coulomb. And again, that negative meant to the left, so let me write that out. And that is my final answer. For part C, we're looking for where in between these two charges is the electric field 0. And so I wrote that as point C, but that's kind of a trick that I'm trying to play on you. It can't be that the point where the electric field is 0 is closer to the bigger charge, because the bigger charge would certainly have a larger influence on point C. It's going to end up being somewhere over here closer to the smaller charge. The electric field from 1 will be directed to the right, and the electric field from 2 will be to the left. And I want them to be equal in size so that they cancel out. And so I can say that E1 should be the same size as E2. So K Q1 over R1 squared has to be equal to K Q2 over R2 squared. Now if I call this distance from charge 1 to that point where the electric field is 0, x, then this distance from where charge 2 is to where the electric field is 0 would be the whole distance of 0.30 meters minus x. So now I'll sub that in, and also I can cross out these k's. So 5 times 10 to the negative 6 coulombs over x squared should equal 10 times 10 to the negative 6 coulombs over 0.3 minus x squared. To make this a little simpler, let me cross these guys out, divide both sides by 5 times 10 to the negative 6. I would get 1 here, and I would get 2 here, and that's certainly easier to work with. So cross multiplying, I get 2x squared is equal to, and when I FOIL this out, I get 0.09 minus 0.6x plus x squared. Bringing it all over to one side, I have x squared plus 0.6x minus 0.09 equals 0. So here we have a quadratic that I'm okay if you plug that into a solver, because I'm sure if everyone had the time, they'd be able to use the quadratic formula to solve. The roots turn out to be negative 0.72 meters and 0.12 meters. And the negative one doesn't make any physical sense here, so we're going to reject this one and say that the distance that we have to be from the 5 microcoulomb charge is 0.12 meters. The next level of complication in these problems is when we have to deal with electric fields in 2 dimensions. In this problem, Q1, which is positive, creates an electric field at point A in the positive y direction. Call that E1. And charge 2, which is negative 18 microcoulombs, creates an electric field down and to the right, which we'll call E2. In order to solve this problem, we're going to need to do a little bit of geometry. So this is 15 centimeters, and this is 30 centimeters. So let's figure out the distance between point A and charge 2. To do that, we do the Pythagorean theorem. We know that x squared plus y squared equals z squared. And so 30 centimeters squared plus 15 centimeters squared equals z squared. And so that distance between the two, charge 2 and point A is going to be 33.5 centimeters or 0.335 meters. Now this angle here is going to be the same as the angle between the x direction and E2, because those are both alternate interior angles. So now let's first try and find the x component of the electric field. So the x component of the electric field at point A, E1 won't contribute to that, but E2 does contribute to it, so we want to take E2 times the cosine of theta. That would be K Q2 over the distance between charge 2 and point A squared. And then cosine theta, we could figure out what this angle is, but we know cosine is adjacent over hypotenuse. And so the adjacent side of this triangle is 30 centimeters, and this triangle is 33.5 centimeters. So we might as well just say 30 over 33.5 as the cosine theta. We can plug in numbers now. 9 times 10 to the 9 newtons meters squared over coulomb squared. 18 times 10 to the negative 6 coulombs. 30 centimeters over 33.5 centimeters. And then over 0.335 meters squared. Putting that into the calculator, I get 1.3 times 10 to the 6 newtons per coulomb. Right, now I'm going to look to find the electric field in the y direction. E1 points in the positive y direction, and E2 has a component in the negative y direction, and I'll have to use the sine of the angle to figure out how much of E2 points in the y direction. So that's K Q1 over R1 squared minus K Q2 over R2 squared sine theta. To make the substitution a little simpler, I can pull out K. So I get Q1 over R1 squared minus Q2 over R2 squared sine theta. Plug in some numbers here. 9.0 times 10 to the 9, 12 times 10 to the negative 6 coulombs. I should put units, newtons meters squared over coulomb squared. Minus 18 times 10 to the negative 6 coulombs over 0.335 meters squared. That 0.15 meters over 0.335 meters is the sine of the angle. And if you put this carefully into your calculator, I'm going to write it up here, 4.2 times 10 to the 6 newtons per coulomb. So here we have our x component and our y component of our electric field. We have to find the resultant of those two components. So from the last slide, we saw that the x component of the electric field was 1.3 times 10 to the 6 newtons per coulomb, and the y component was 4.2 times 10 to the 6 newtons per coulomb. And so now we're trying to find this resultant here, the total electric field. We need to find its magnitude and its angle. To find its magnitude, I'll use the Pythagorean theorem. So I get a magnitude of 4.4 times 10 to the 6 newtons per coulomb. Now I want to find the angle, so I'll do tan negative 1 of opposite over adjacent. So that's the 4.2 times 10 to the 6 newtons per coulomb over 1.3 times 10 to the 6 newtons per coulomb. That gives me an angle of 73 degrees. And so now I need to write my final statement that says that the electric field is 4.4 times 10 to the 6 newtons per coulomb at an angle of 73 degrees, and this would be above the positive x-axis. For this last part, we're trying to figure out the electric field at point B. This one's a little bit easier because if we bisect this 30 centimeters, and then we draw our R in, so this would be R1, and this would be R2, we could see we have congruent triangles. The electric field from the 12 microcoulomb charge would be up and to the right. I'll call that E1. And the electric field from charge 2 would be down and to the right. And it would be stronger than the electric field from 1 because they're equidistant, but charge 2 is bigger than charge 1. Now the process for solving this is going to be really very similar to finding the electric field at part A. So I want you to take a few minutes and see if you can do it. And then on the next slide, or in a minute on the YouTube, you'll be able to see a picture of the solution. In this lesson, we learned how to define an electric field, draw electric fields for common charge configurations, analyze a charge's behavior between parallel plates, calculate the electric field created by a system of charges in one dimension, and also in two dimensions.